All right, it's a pleasure to be here. Can you hear me well? Okay, good. And if at some point what I'm writing is too small and you can see it in the back, just wave and I'll try to write bigger. Well, it's a pleasure to be here, and I understand I am talking to a mix of computer scientists, mathematicians, and economists. What I'm going to talk about, sort of my focus, given also the theme of the conference, is going to be on matching. Matching is the most central problem in algorithm design and computer science. Its roots goes back to the work of Euler and Kirchhoff, and at every stage of the development of theory of computing, for example, when Edmonds wanted to write his first paper on finding matchings in general graphs, he defined this notion of noise algorithms, what we call these days polynomial time algorithms. Or later when Karp developed this framework for intractable problems, the problems we call now NP-complete, one of the examples was three-dimensional matching. And now, with the advent of marketplaces, online marketplaces for the allocations of goods and services, we are being challenged every day to sort of advance the state of the art for the development of algorithms for matching. This is something that I've been thinking about for the past 10 to 15 years, and I'm going to tell you a few examples of what I and quite a few people in the audience have been thinking about. It will be also sort of a critical view of the competitive ratio. Another interesting thing about this sort of new applications of online matching in different domains is that it has challenged us to look at some of the dominant and sort of common ways of designing algorithms and analyzing algorithms to make them more useful in practice. Specifically, the one problem that I'm going to look at today is the online stochastic matching problem. So let me write it here. In this problem, you're trying to find a maximum weight matching in a bipartite graph. One side is offline. These are a set of offline nodes. These are the nodes, sort of they're waiting to be matched, and then you have online nodes arriving. Let's say online nodes are going from sort of 1 to t. Offline nodes are 1 through n. At time t, with probability pt, node t arrives. Let's say the bipartite graph is given to us. So for every node t here and for every node I, we know the weight, the value we gain from matching I to t. So once the node arrives, we have to decide how to match. So you have to decide whether you match this node, and then if you match this node, who to match it to. And then the goal, maximize the weight of the final matching. And I should say right off the bat, if you have any questions, please raise your hands, and if something is not clear, ask questions. So at time 1, node 1 arrives with some probability P1 that's given to us. You look at the node, you look at the offline nodes, you decide who to match to, and then node 2, and so on and so forth. Good. So what is, there is like one special case that is worth mentioning. Let me write that too. Imagine you have only one offline node. So let's say you have one node here, and then let's call it node 1. And let's potentially, T nodes are arriving with probability P1, P2, all the way. So let me make an example. Let's say first node arrives with probability 1. The weight of the matching is 3. The second node with probability half, it's 5. This is a quarter, 1. Another quarter, 1. That's good enough. So this is like a sometimes called online Bayesian selection. Imagine you have one item that you want to allocate, one item you want to sell. Buyers show up, and you want to allocate it to one of them. So it's like online Bayesian selection. One notion that's going to be important for us, and it's also in the title, is the competitive ratio. It's the worst case ratio of the solution of the algorithm over optimum offline. So you can come up with some algorithm, some online algorithm for allocating this. And then once the process ends, you can look back, and then you can look for the compute the maximum weight matching, and then look at the ratio of the two. That's the competitive ratio of your algorithm on that particular instance. The competitive ratio in general is defined over the worst case instance. So here, what is the optimum offline? Well, if I know which vertices are going to arrive, I can take a look and see if the second vertex arrives with probability half, I'm going to allocate to that vertex. So I'm going to get half times 5. And if that doesn't arrive, I'll give it to the first vertex. So I can get, half times 5 plus half times 3. That's like roughly 2.5 plus 3 over, that's like 4. But for an online algorithm, that's not possible because you can't predict, So for example, one reasonable online algorithm is when this vertex arrives, you don't take the risk. You just allocate it to the very first vertex. That way you will get value of 3. That's 3/4 of the optimal. So now you can ask what is the best algorithm that can obtain the optimum competitive ratio. And this is a result that goes back to 70s. That in the case of one offline node, so for the online Bayesian selection, so what is known, this is like a classic result. For one offline node, the best competitive ratio possible is half. So you can get half of optimum. This is a result of, and I have one cheat sheet, and that's references. KSG78. It's also known as a profit inequality. I think that's what the authors call this. So the idea is that there is this prophet that's omniscient, that can see into the future. And because of that, it can sort of make decisions optimally. But now, mere mortals, we can't really see into the future. We have to make these decisions sequentially. How can we compare ourselves? The best algorithm versus the, sort of the prophet. And the, lovely result that they had was that you can get half of the optimum. This is later generalized to the, maximum rate matching. So you can even get half competitive. For this case, for the maximum rate matching, and that's more recent. So let's see, there is a FGO, Feldman et al. And Ezra et al. So that's 14. And EFGT 20. They managed to generalize it to the case where you have n offline nodes and t online nodes. And there is actually a lot of follow-up work on this. So this was for one item, this is for matching. You can impose other combinatorial structures. What if you have multiple items that are exactly the same? What if you have an underlying, Metroid constraint on the, sort of your allocation, or downward closing sets? There are many, many papers on this, various profit inequalities for various combinatorial optimization problems. And this is now the time that I'm going to be fancy and move this up, and then move this up. Wow. And tell you, sort of one common way of proving such results is to write a linear program that captures the optimum offline. So in the case of matching, I can write the following. Maximize. Actually, let me write it here. Maximize sum of, say, I and t, wit, xit, such that sum of the xit over I is less than or equal to pt. This is for all t. Sum of xit summed over t is less than or equal to 1. That's for 1i. And xit is bigger than or equal to 0. Right? This vertex t is going to arrive with probability pt. So if you look at, if this is the probability that the optimum algorithm allocates the arriving node t to one of the offline nodes I, well, it can't be more than the probability of the arriving. And this just says the capacity of every offline node is 1, and that's just, xits are non-negative. So you write such a linear program, and then these online algorithms essentially give you a way of rounding that linear program. And, sort of, it's not hard to see that half is the best possible for both cases. And here is an example. imagine you have one offline node, two online nodes. The first online node arrives with probability 1, and if you match it, it will give you, value of 1. And then the second node arrives with probability epsilon, and then if you match it, you get 1 over epsilon. So if you can see into the future, you can check whether the second node arrives. It arrives with probability epsilon, and then you gain the value of 1 over epsilon. So optimum offline is epsilon times 1 over epsilon plus 1 minus epsilon times 1. That's 2 minus epsilon. If you can't see in the future, you either match in the beginning and you will get 1, or you wait and then again expectation you get 1. So the optimum online, the best thing you can do if you algorithm designer is 1, right? So any algorithm is going to be getting you value of. So essentially half is the best is the best possible. This is true for the special case, so therefore it's true for this matching problem. You can write this this linear program. The integrality gap of this linear program is also 2. Such a pretty picture. It seems like we have found the solution. LP, counterexample, algorithms. Why do you want to mess that up? Right? I should conclude my talk here, and we all go home. So it turns out, the challenge with this sort of competitive analysis, even though it leads to nice math and elegant math, and it has been sort of very popular in theoretical computer science for the past 30 or 40 years. You search on competitive analysis on Google Scholar, you get thousands of results just for matching. But the challenge is that because we are comparing ourselves to this prophet, to this sort of omniscient being that can see through the future, no algorithm that's designed by us mere mortals can really compete. So in this case, we are actually lucky that we can get half of the optimum. In some cases, it's like sort of the ratio of optimum online to offline goes to 0. And because this benchmark that we compare ourselves against is so far away, most of the algorithms look the same. Like nobody can get better than half. And maybe even sort of worse, because we are assuming that the input is worst case, and sort of there is this adversary that's trying to design this input that's going to beat our algorithm, the algorithm's choices are going to be very conservative. Because you really want to compare yourself against, sort of this all-knowing person in the worst possible case. So you come up with this nice, simple algorithm, but once you want to implement it, you will see that they don't do that well in practice. There are quite a few experts in the audience. I'm sure Flor is going to talk about some of her experience, in that in that area. So our hope is to do better, and come up with a better benchmark that's a little bit closer to reality, and see if we can do if that leads to the design of better algorithms. So for the rest of this lecture, I'm going to put more focus on the optimum online. So imagine that you actually there is some algorithm that can't see the future, but potentially has a lot of computational power. So this notion of optimum online, it's not new. It goes back all the way to Bellman, if not before, and it's sort of. When you have decision making with uncertainty, and some people will argue that's the essence of life, it's sort of Bellman's equation gives you one way of modeling the optimum decision. So the way it sort of moves forward is, so let me define this optimum online, the best online algorithm. You can write this concept of value to go. So it says, imagine you're at the step T of the algorithm, and set S is the set of nodes that are not matched. And now you want to decide what to do. You have a bunch of options. So first of all, with some probability PT, let's say probably 1 minus PT, the vertex is not going to arrive. So you just move to T plus 1. And then with probability PT, online node T arrives. Then you have a bunch of choices. First, you can decide whether to match T or not. So this will be V of S comma T plus 1. If you're still, it arrives, but you don't match it. Or you take this maximum over all I that is adjacent to T. Well, let's say over all I. Where is my eraser? So you decide who to match it to. So in that case, you will get V of S minus I T plus 1 plus WIT. Did I get it right? So say it one more time. This is when T does not arrive. This is the case where you don't match T. This is when you match T to I.
Maybe the max of I and S to here and T.
Oh, thank you. So at least, someone is paying attention. That's a good thing. Now, naively, if you want to implement this, you need to look at, sort of have all of these subsets as your, essentially keep track of which vertices are matched. That's exponentially many, right? So this, if you want to implement it naively, it needs, takes exponential time. Now, what if you only have polynomial time? What if you're looking for the, sort of an efficient algorithm? So here is the major, sort of the main question of the talk. What is the computational complexity? Or complexity of optimum online. By the way, optimum online is when you start with at time 0 and S is everything, right? You start with at time 0 and you have all the vertices available to you, and then you solve this sort of recursion or write the corresponding dynamic program. How hard is it to approximate V of S of T? That's the focus of this talk. Yes, sir?
Just one question, why is it optimal like this? Why do you take the max over I of
better for some other vertices, no?
Yeah, so I'm taking the maximum over the whole thing, right?
Yeah.
So here I'll sort of match t to I, and I gain some value. That's WIT, as you mentioned. And this is the value to go. This is the value that I will get sort of in the future. So if I drop this, then what?
You know that the WIT are much better for the other S.
For other I, right. So there may be some, right, maybe this vertex arrives, and I have two choices. One of them is better, but if I match it to the one that is better, I will lose in the future. Because who knows, maybe in the future some other vertex arrives and it has a sort of WIT of 1 billion. So I want to reserve this. This captures the future value. This captures the current gain. Yeah. And I'm adding them up, and I'm sort of taking the maximum over the long-term horizon. Excellent question. Thank you. So what is the computational complexity of optimum online? That's sort of something that we have been, and with a few people in this audience, we have been focusing on, and that's what I'm going to talk about. So I'm going to move this all the way up. And then let's see if I can bring this down. So what I'm going to do in the rest of the talk is going to, I'm going to show you a whole bunch of algorithms that do better, sort of give you a better approximation ratio compared to the competitive ratio of half. So essentially, by reframing the problem and by writing it as sort of approximating optimum online, we move the problem from the realm of competitive analysis to the realm of approximation algorithms. And there are a whole bunch of techniques in the design of approximation algorithms that now we can take advantage of. So first, the computational complexity, and this is something that I started working on with Christos Papadimitriou, and eventually with Tristan, who's sitting here, and David Weitz, we managed to nail it. So this is theorem 1. P, that's Papadimitriou, Tristan Polner, me, and David Weitz, 2 and 1. There exists an epsilon such that it is P space hard to approximate optimum online with ratio better than 1 minus epsilon. So P space hard is a notion of complexity that's a little bit harder than NP hard. So it talks about all algorithms that need polynomial space. So it turns out that unless P space is equal to P, you cannot, not only you cannot compute the optimum online, you cannot get close to it. So this essentially rules out polynomial time approximation algorithms or fully polynomial time approximation schemes. I don't know, epsilon is like what, 0.001?
Much smaller.
Much smaller, so 10 to the power.
I don't think we even computed it. I'll say, I think if you just want to show NP hardness of approximation, then maybe it's like 0.01, 0.001, something like that.
I see, yeah. So it just says, you know, so you cannot get arbitrarily close to 1. There is a threshold. And these are, you know, sort of usually using, there is this canonical p-space hard problem called a stochastic SAT. So like, you know, think about typically when you have a satisfiability formula, you're given a Boolean formula and then you need to set values true and false to the Boolean variables to, you know, sort of, let's say, maximize the clauses that are, you know, sort of satisfied, or you satisfy the Boolean formula. In the stochastic SAT, it's essentially a game against nature. So let's say if your Boolean variables are x1, x2, all the way to xn, you set x1, then nature tosses a coin, sets x2 to true or false, then you set value for x3, then nature tosses a coin and says x4 is either true or false, and so on. And then your goal is to maximize the probability that your function is true at the end. This is called the stochastic SAT. These are, you know, sort of called games against nature, and they're proved to be p-space hard. This is actually a paper by Christos Papadimitriou, I think in the 80s, that proved that. Later on, a whole bunch of problems are proved to be p-space hard. As far as I know, this is the first, you know, sort of combinatorial problem in which the offline version is polynomial time computable, but the sequential version is actually p-space hard. And also this sort of, you know, stochastic SAT is giving you a, you know, sort of a sense of the type of problems we are dealing with. In competitive ratio, you're designing an algorithm against an input that's adversarial, that's designed to beat you. Here it's game against nature that's tossing coin. It's like nature is oblivious to you. They don't care about your algorithm. It's just, you know, sort of setting this input according to some stochastic process, and just you're trying to, you know, sort of come up with an algorithm that optimizes the performance. Yes?
In this setting, why do we look at the ratio and not just additive error of epsilon? Did it convert that theorem to an additive error?
Yeah, you know, sort of, I don't think it's makes a huge difference. You know, you sort of, then, you know, sort of you will set the WITs to 0 and 1. There are a whole bunch of open problems that I'll get, you know, sort of to you at the end. For this special case, you know, sort of where you have the weights and when the arrivals are non-stationary, we can prove p-space hardness. But there is a wide range of problems where we don't have a proof, and I think, you know, sort of, but I suspect they're all hard. Good. So this is hardness of approximation. How about algorithms? When it comes to algorithms, there's been actually a lot of progress, and I have to look at my cheat sheet again. You'll see why. So when we came up with this, and, you know, sort of this appeared in 2001, just to show that, you know, optimum online is a different benchmark from optimum offline, we gave a 0.51 approximation algorithm, so better than half. This is again PPSW. Then it was improved shortly after to 0.526. That's a result with David White's. Then, you know, sort of next year, you know, same conference, it was improved to 0.632. That's 1 minus 1 over E. This is Mark Braverman, Mahsa Darakhshan, and M is Antonio Molina. This is 22. Then it became, you know, by NSW, that's David Weitz and co-authors, to 0.65. And then in 2003, we have 0.671. This is a union of several of the authors there, BDSPW23. Now, these numbers are not super important. What I'm trying to show you is that this is a very active area of research. Many of them are at Stanford, Technion, and a whole bunch of people at Princeton. So they're all, we're all trying to push the envelope. And I will make a case to you that by moving from this competitive ratio to coming up with algorithms for approximating optimum online, we have managed to sort of move away sort of beyond the simple algorithms and use a lot of very interesting techniques that sort of in the end come up with actually more interesting algorithms. Obviously, I'm not going to show you all of these results. I'm going to try to give you a sense of this. I'm going to show you the 0.632. The algorithm that I'm going to show you is not exactly the algorithm that Mark Braverman and Massa sort of came up with. I'm going to show you a simpler algorithm and a simpler proof that gives you 1 minus 1 over E. And then Tristan tomorrow is going to present you this one. So you can consider sort of my talk as the sort of the opening for Tristan's talk. Yes?
Do we know if the approximation algorithms dominate the competitive algorithm?
Say it one more time.
Do we know if these approximation algorithms dominate the competitive algorithm?
Dominate in what sense? In terms of competitive ratio, those algorithms are optimal. So they can.
The expected reward.
In terms of the expected reward on what instance? You have changed the benchmark, right? So it's not super clear how do you compare the two. But I'll show you the algorithm, and you'll see that sort of there are some sort of new ideas, and and I'll later talk about some of the sort of implications of this way of thinking when applied to real data. So I'll point out sort of about some work that I'm doing with Anders that's just sitting in that corner. And you can ask him more about sort of the progress applied to real data. Yes, sir?
All these algorithms are polynomial time.
All these algorithms are polynomial time, yes. If you allow me exponential time, I'll solve that for you. So.
But nothing in between.
Excellent. That's a very good question. If I have time, and I have 20 minutes, I'll talk a little bit about coming up with super polynomial time algorithms. So, and that's an excellent question. One of the reasons I became interested in sort of this question of approximating optimum online is that this type of problems have a lot of applications. So think about applications in the context of online advertising, ride sharing, or sort of matching kidneys to patients. With all of them, you have one side waiting, like advertisers or sort of taxis or people who need kidneys, and then the other side arrives and you have to make sort of decisions. And then you go talk to people at Uber or Lyft, and they tell you if they manage to make an improvement, sort of by 1 or 2%, there are heroes in the company. And here, we come up in the context of competitive ratio with an algorithm that's, half optimum in the 70s, and we consider it, done, and we want to go home. So here, once you have such a framework, you can actually think about the, sort of the boundary between polynomial time and exponential time and say, if you have more data, if you have more computational resources, can you get closer and closer to optimal? And if there is time, I'll show you some of these ideas of coming up with linear program hierarchies that can try to get closer to the optimal. If there is no time during the talk, I'm happy to tell you after that. So, excellent question. But I only have 15 minutes, and I want to show you at least one algorithm. So let's do that. So look at that linear program in the corner, and it captures perfectly optimum offline, right? It doesn't, sort of say anything optimum online. So if I'm going to add one more constraint that captures one of the properties of the optimum of an online algorithm. So it says xit is less than or equal to p sub t times 1 minus sum over t prime smaller than t xit prime. So think of xit as the probability that your algorithm allocates t to I. Well, in order to allocate t to I, well, vertex t should arrive. So that's probability pt, and I should be available. What's the probability that I is available? Well, it shouldn't be matched to anything else. So that's 1 minus xit prime, t prime is smaller than t. And these two events, for an online algorithm, these two events are independent from each other. Because when you're making allocations up to time t, you don't know when the t is gonna, when node t is gonna arrive. Yes?
Just have a question about this algorithm. Are all of them still 1/2 optimal?
You're,
I mean, if you compare them to the optimal offline, are they still 1/2 optimal against the optimal offline?
I think so, but good. Tristan
One
knows.
thing you can do is if you have a half competitive algorithm and you also have, let's say, 0.671 approximate algorithm, you can just take the better of the two. You can efficiently approximate how well each of them does and then get sort of this best of both worlds.
I see. Right. You can run in Monte Carlo on the side. Yeah. Good. Okay. So that's without loss. Is this clear? Now, for an online algorithm, these two events are independent. But if you're omniscient, if you know what's going to happen in the future, then you can make your allocations, sort of differently. So this independence is only true for online algorithms. So this is only true for optimum online and not optimum offline. So this is a better linear program that captures optimum online. I'm going to assume that we're going to solve this linear program, and then we're going to, sort of round it. And it's going to be instructive to do it probably first just for when you have one offline node. So let's look at that special case. So here it is. At time t, if t arrives and node 1 and node, remember we have only one offline node, I named it node 1, is available. Match with probability well, I want to use the optimum solution of that LP. Typically, you would write x, 1t a star, but I'm going to drop the star, x1t over pt times 1 minus sum of x1t prime, t prime smaller than t. That's my algorithm. So essentially, I'm trying to, I'll solve this, I'll get the x1t's, and then my online algorithm tries to capture the same marginals. So my online algorithm is trying to make sure that I match node t to 1 with probability x1t. So I'm saying with some probability this is not going to arrive, with some probability this is not available, so I'm normalizing by that. So the claim is that this rounding is actually lossless. The approximation ratio of this algorithm is 1. So claim t is matched to 1 with probability x1t. So you solve that linear program. That linear program is an upper bound on the optimum solution. And I'm going to give you an algorithm that gives you exactly those marginals. So this means that my approximation ratio is 1. You can prove this with induction. Imagine this is true up to time t minus 1. At time t, what's the probability that I match? Well, in order to match, node 1 should be available. What's the probability of that? 1 minus x1 t prime is smaller than t. This node should arrive. What's the probability of that? pt. Then what's the likelihood that I do the allocation is this one. x1t over pt 1 minus x1t prime. So this is canceled with that. The probability that I allocate 1 to t is x1t. So solve that LP. I'll give you an algorithm that implements the solution of that algorithm without any loss. So this is a lossless rounding. So with respect to competitive, sort of the optimum offline, I can't get better than half. With respect to optimum online, I'll get you the optimum. All right, this is going to go up. I'm messing something up. Oh, there you go. I can't do both at the same time. This is. These buttons are challenging my jet lag brain. This was the All right, how about the more general case? I can build on that idea. So the difference here is that when the node t arrives, there may be multiple offline nodes, multiple eyes that are potentially interested in that node. So I have to do some type of optimum conflict, online conflict resolution. So for every t, every I requests t with probability the same as before. xit over pt times 1 minus sum of xi t prime is smaller than t. So t arrives, every node makes the same calculation and says, they want this node. This is similar to before. If at every point only one, when the t arrives, only one asks for t, then I can allocate it and I can give you the optimum solution. But we know that's not going to happen. That's why I can't give you the optimum. So I have to do the sort of contention resolution. And this is the way it's going to be done. If t arrives, allocated to of all the requests. So let's say R is the set of nodes that are making the request, allocated to maximum WIT I in R. So I look at, who is making the request. One of them, sort of is giving, has a higher weight for matching to this node T. I'll allocate it to that person. Everyone else, too bad. And I can run this algorithm. And then I can try to do some kind of analysis like the one that I showed you up there. And this is essentially what BDM tried to do with some, but one challenge with this algorithm is that when you look at the state of the offline nodes for, different eyes, there is a lot of correlation that's happening. Because, some of these nodes are making requests, and whether or not your request is accepted depends on other nodes and their states, whether they were available or not. I guess every eye that is available, that's available. If they are matched, then they don't make any requests. And this becomes an algorithm that's very hard to analyze. So I'm going to do something that may look wasteful, but it's going to make our life a lot easier. So for every other node, discard I with probability PT. So the node T arrives, a whole bunch of nodes make requests and say, we want to get matched to T. The one that has the highest weight, I match it to that. Everyone else, regardless of whether T arrives or not, for each one of them, I toss an independent coin, and with probability T, I throw them away. Now, why is this an interesting trick? Because look from the point of view of one of the vertices, this one of the eyes, one of the offline nodes. You make a request, and with some probability, you get matched, or you get discarded. And that probability is PT. And that's independent of the state of every other node. So essentially, I have managed to introduce this independence between the states of the various offline nodes. And that helps my analysis. Is this clear? So let me define this random variable FIT that says node I is available, meaning unmatched, and if that's a word, undiscarded. At time t. FITs are independent from each other. So essentially, with this way of rounding, I don't allow any communication between the states of the nodes. When you're a node I and you make a request, you get matched or you get discarded with probability PT, independent of everyone else. Once you do this rather wasteful and artificial thing, it makes the analysis a lot easier, and I can write the analysis maybe here with rather quickly. So let's see what is the probability. Let's say WT is the value of match of the match of T. So I want to know what's the probability that W is bigger than or equal to WT. Well, in order to, when the node T arrives, it matches to some node with I with WIT bigger than WT, it needs to get a request. So first of all, it has to arrive. And then in order to get a request, well, I have to look at the probability that none of them make a request. So this will be all I such that WIT is bigger than W. And for them to not make a request, either they have to be, sort of shouldn't be free, and then, well, then make a request with probability xit over pt times 1 minus sum of xi t prime is smaller than t. Now this cancels with that by definition. So this becomes pt times 1 minus product of wit bigger than w, 1 minus xit over pt. And this is a common trick, sort of to write this 1 minus xit over pt as e to the power minus xit over pt. And then this is 1 minus e to the power minus sum of those. So you can do the algebra. This is bigger than or equal to 1 minus 1 over e sum of xit wit bigger than w. Now, this is the probability that the match is bigger than, wt is bigger than some w. You integrate over both sides, and what it will imply, and I'm sorry that I'm writing this in the corner, implies that expected value of wt, essentially the expected gain from the tth matching, is equal to sum over wit xit. Well, it's bigger than or equal to 1 minus 1 over e. Right? You get this by integrating over w over both left and right hand side. That will give you the 1 minus 1 over e approximation algorithm. And I'm sorry, I wanted to make sure I do some calculation for you, but I realized that may take a few minutes to absorb. Leave it there. Maybe during the coffee break, you can take a closer look. That gives you the 1 minus 1 over e. And as I mentioned, this is a wasteful allocation. And then you can start thinking about, why am I discarding all these vertices left and right? Maybe I can sort of do something better. And that's the basis for the follow-up that Tristan is going to talk about. Instead of sending these proposals independently, he's going to try to incorporate some sort of negative cylinder dependence between the proposals and get from 0.632 to 0.671. And as you can see, there is still a sort of a large gap between hardness of approximation and the best ratio we can get. So I'm expecting there will be a lot more technique, a lot more ideas to get the lower and upper bounds closer. So let me conclude with a bunch of pointers. And I have 1 minute for pointers. So one, maybe the most important one, sort of Tristan's talk. Sort of better algorithms and better analysis. Then we have been sort of looking at coming up with families of linear programs. So here I just added one constraint. And one constraint can only buy you so much. Maybe we can come up with bigger and bigger linear programs and get closer and closer to optimum solution. So this is something that I have been thinking about with Ali Reza and Ali. Both of them are actually going to speak. Ali Reza, I guess, right after me, and Ali in the afternoon. So with Ali and Ali Reza, maybe sort of hierarchies of linear programs, or sort of very large. What do we call them? Hierarchies of linear programs. Yeah, like hierarchies of LPs. And one interesting sort of variation of the problem that I didn't discuss, I assume you have these online nodes that are arriving and they're very impatient. They have to be matched right away. And then the offline nodes are infinitely patient. They're going to wait until they get matched. Imagine, sort of the offline nodes, if they don't get matched for a while, they disappear. So there's this, sort of, say, Poisson clock that tells you after, sort of sometime they go away. There is this paper by Ali and Awad and Seritak that looked at this problem a few years ago, I think 2020 or 2019. And say again? Oh, and he's going to talk about it this afternoon. I think, again, there is a lot more to be done. It's one of my favorite papers in this area. And then finally, I assumed that the input to this problem is given to me, in the sense that somebody is going to show up and says, at time t, this node is going to appear with probability pt. Now you ask people who's going to, sort of give you that, and they say, oh, there's some machine learning people, data scientists, they're going to figure that out and then give it to us as input. Well, that's a dream. Rarely it comes true, sort of. So this idea of this delineation, that there is a learning that comes up with, sort of the input to your algorithm, and you're the algorithm designer, and then you come up with an algorithm based on this input. I think, sort of, we have to remove that boundary so we can try to, sort of think about learning the optimum solution. Learning the optimum algorithm. And there is this paper that we are working on. And you have to remind me, Anders sitting in that corner is one of the person who's essentially leading the charge. It's with, so it's with Anders, it's with Ellen Witersek, and it's with Alexander, that's H, right? Yeah. Okay, and it's forthcoming. So here, we do two things. We look at families of instances in which that value to go function, that I don't have it here, has this local structure. So in the sense that when you want to compute the value to go, maybe you want to compute the value to go to decide you want to match this node to one of the, let's say this passenger that has arrived to one of the taxis. Maybe the problem has some local structure. So you don't need to go look far away, vertices that are far away in the graph and look at their state to decide who to match to. Maybe by looking at a radius of, sort of r for some constant r, and look at the configuration of which nodes are matched and which nodes are not, you can decide what is approximately, sort of the best decision to do. And that's something that we are doing. And then on top of that, you may say, maybe this input of who is going to arrive is not given to me explicitly. It's something that I want to learn over time. So actually, sort of Anders and Alexander have managed to train graph neural networks that learn the optimum solution. And he can tell you the solutions are actually, so the results are very promising. We can do significantly better than heuristics like greedy by 70% or so. What's the number?
I think we could do like 40%.
Only 40%. All right, with that, I conclude. Thank you so much.